let me introduce myself. My name is Gaiman Yee. I'm the Technical Director of the I4 Energy Center. Welcome everyone to today's I4 Energy Seminar. Today's speaker is Tom Webster. Tom is a research specialist at the Center for the Built Environment here in Berkeley. He has been engaged in building energy controls and communications R&D for over 20 years. His experience includes commercial and residential HVAC systems engineering, distributed control systems design, digital controls product development, and building energy analysis and simulation. Tom received a BS in mechanical engineering from Berkeley. And Tom is an old colleague and friend. He and I worked in a small controls company back in the early and mid-1990s. And he is sort of responsible for me being here today. Back in the recession after 9/11, I was laid off, and Tom helped me get some work at the Lawrence Berkeley lab. He and I collaborated, and we ended up with 2 articles in a published book. So, let's see. Oh yeah, so that gave me some breathing room until I got hired at CIE. So let's welcome Tom.
Okay, can you hear me all right? Okay, great. Thank you, Gaiman. Yes, that was quite a history we have there. It's actually the other guy that's involved in that is right here, Ron Hoffman, of course, because he was our boss in those days when we were trying to invent digital control systems, actually. So anyway, I should point out this poster right here. This is actually a paper copy of it. It's back on the back wall if you want to get up close and personal to it. This is just an overview of what we call our wireless PMP toolkit. That's kind of our working title of it. So you can look at that later if you like. I'm going to be covering this in quite a bit of detail today. So anyway, today I'm here to talk about building performance evaluation and how wireless sensing can help us do it better, faster, cheaper, and get to where we need to be with performance assessment of buildings. So I think most of our team is here actually, so if you guys have any really technical questions, you can ask these guys. They're quite smart and capable, so that would be great. Also, I'd just like to acknowledge kind of our collaboration going on 2 levels here, one with the EECS department with Andrew and Stephen here. They've done a fantastic job helping us along the path, and I'll talk about that later, SMAP in particular. And Fabian is helping us on the hardware side, and we're also talking with Stephen Lancicera at LBL. Who's doing similar kinds of things up there. So anyway, this is a little overview of what we're going to talk about today. Who and what is CBE? History of performance measurement carts, basically. Performance monitoring methods and tools, and how it all works. And then I'll tell you a little bit about where we're at right now and where we're going. So how many people here know about Center for the Built Environment or have ever heard of it? Hey. Oh, not you CBE people. Come on. Anybody that's not CBE, please raise your hand. Okay, a few. Okay, well that's good. Anyway, we're a small group in the architecture department, and we do the building science part of architecture. Our director is Arens, who is here, and you can go to our website here to see a lot more about what we do. Lots of cool things on there. But generally, I just want to give a very brief overview of the kinds of things that we do, which is really studying buildings, trying to advance the development of new technologies, developing tools, various kinds of tools to support these efforts, and contributing to standards and guidelines. And so in that, the way we accomplish this, of course, is we do lots of field studies, we do surveys, we do simulations, simulation model development, laboratory testing, and develop new products. The most notable one, of course, is wireless lighting control system that Charlie Huizinga took out and started a company called Adura Technologies. You've probably heard of it. That was initiated in our shop, basically. And now Ed and his group is working on a personal control system that you see the two major components of it right down here. Very, very promising technology there. And then lots of tools. You can go on our website and see these various kinds of tools. Thermal comfort model, very sophisticated way to model the thermal performance of a person, thermal comfort of a person. We have some web-based calculators, design tools, all kinds of things. So anyway, that gives you a basic idea of what we're about at CBE. I should say that it's a consortium. We have 42, I think the number is, thereabouts, of industry partners, and these are all flavors from manufacturers to agencies to architects and engineers and contractors. So here's a little brief history of carts, portable carts. And so when I say carts, you'll know what I'm talking about from here on, because that's the way we talk about these things, even though it's not very sexy or sophisticated. We think about it that way. Anyway, these are three models of some carts that were developed way back when, probably before some of you were born. And up through this later versions in 1990 that were used primarily for research on thermal comfort. So these measure all the basic parameters needed to evaluate thermal comfort, and they're automated data collection systems on it and everything. So very, very important work was done with these carts early on by CBE. And then we're going to go switch to fast forward to 2006, when we had the great opportunity to take our cart technology to one level up to the next generation. But first, I need to introduce this a little bit. This was a project that came about because of the New York Times was building this new headquarters building in Manhattan, and they had an underfloor air distribution system in it, and they needed a way to commission that. So they needed a device to be able to do that. So now, how many people know what underfloor air distribution is or have heard of it? A few. Okay. So I'll give you just an overview, because that'll help you understand why we built the device that we did. Underfloor air is really, you can think about it as an air conditioning system, a regular air conditioning system turned upside down. The air is now delivered through the floor rather than through the ceiling, as it normally is, like it is in this building, for example. And so there's a raised access floor here. Air is delivered underneath here, and it comes out of these floor diffusers here. And lots of interesting variations of this, but this is the basic idea. So this is one example of there's two important aspects, and one of them I got to show here, unfortunately. I misplaced that slide. So two key aspects of this is stratification and what happens in the supply plenum. So I'm showing here a height versus temperature diagram here, and showing how the temperature varies with height here. So this is a characteristic of an underfloor system. So we need to understand that. We need to be able to measure that to understand the performance. Likewise, in the underfloor plenum, there's lots of things going on with how you put the air in there and the consequences of that. And these are some CFD diagrams showing what happens when you do it in various ways. And so you can see you get temperature variation all over the place here. Very hard to predict this in real life. So we like to actually measure that. So those are the two kind of key parameters that we're looking for to go after. And so building this particular device is what we're trying to accomplish. So you can see this cart here now has a telescoping mast here that has thermocouples on it to measure the stratification profile. It's hardwired to these I/O ports, I/O devices down here. And then there's a pressure sensor here to measure underfloor pressure and its temperature as well, actually. And all this data goes into this PC here. Well, in order to get the next part, the temperature distribution in the plenum, we went up to, this is our first introduction actually to wireless mesh networking, because that's a perfect opportunity for us to measure the temperatures in the plenum simply by putting a moat in these diffusers here all across the floor plate. So we did that in the New York Times, and here's a diagram of how we distributed 70 of these moats over this 18,000 square foot floor plate. And you can see a temperature scale here that shows what this temperature variation in this plenum is all across that floor plate. So now we have both sets of information simultaneously, all rolled up into a database on the laptop, all run by LabVIEW software. There's lots of support for testing, conducting tests and whatnot, as well as some analysis, which is really shown on this page. One view of analysis where we actually went to the level of evaluating the data we're getting and putting a pass-fail test on it, basically, which was one of the requirements that they had. So the idea is that a less skilled person could actually go out and take these measurements and understand what's going on and whether the system is performing correctly or not. So now I'll talk a little bit about performance evaluation. And so why are we interested in performance monitoring? Well, as you all know, we've got quite a problem with climate change and the consequences of using too much carbon. And building energy is a key part of that, of course. And around that, there's lots of things going on, as you probably know. Legislation happening, there's new labeling programs, certification programs, all kinds of things that are happening around buildings in this regard. So this is really fostering a whole new level of performance checking and verification. And it also requires a lot more in-space measurements now than we ever did before. All of the what we call indoor environmental quality sensing, I'll talk more about that in a minute, now needs to be done in order to ensure that we're delivering comfort and health as we're reducing energy use. Also, as I showed, there's many variations in system types out there, and some of them have these asymmetrical environments, so that's a more detailed set of analysis that we need to cover as well. And of course, all buildings have issues. We haven't been in a building yet that we didn't find something that was amiss, and that comes about from a whole host of reasons that I won't go into in any detail, but it's just a given fact. And of course, that means that you need to diagnose, you need to commission, you need to fix things, and so you can improve the comfort and energy performance. And we need standardized methods to do all of this, and we need an efficient, standardized way to assess these buildings. So that ushers in this particular thing. You may have not heard of this performance measurement protocol, the PMP, which was developed by American Society of Heating, Refrigeration, and Air Conditioning Engineers and some other groups here. And this is becoming kind of the standard of the industry of how to do these assessments in a standardized way. So it embodies measuring at 3 levels of complexity, from a very simple level all the way to a research level, which is, highly intensive instrumentation that you need for that. And it covers these basic categories: occupant satisfaction survey, again oriented around IEQ issues. I'll talk about that. I'll show you a lot about that in a moment. that was developed by CBE. And then energy is basically done by using the EPA Energy Star rating system. Very effective, probably kind of the state of the art of doing this, at least on a gross building level. There's water use standards, and then there's all the IEQ measurements that are shown here: thermal comfort, lighting, acoustics, indoor air quality, that all need to be now measured. That we really hadn't been doing much of that before except as research projects. So what we really need is some, and what's lacking is some easy to use tools to make this all happen, because if we don't do that, it probably won't happen. It'll just be too expensive and unwieldy to be practical. So our goal here is to make it practical and easy and efficient. Okay, so I'm going to step through those basic categories now and talk about each one in a little more detail. So this is the introduction to the IEQ part, and you know, our goal in life, of course, is to make all these people happy while we're saving energy. But this is what our Occupant Satisfaction Survey is all about. This is a web-based survey that people in the building can take in 15 to 20 minutes. Answering a series of questions. It can be used now for benchmarking, trend analysis, and commissioning and diagnostics things, as well as many other things, actually, because there's a lot of data here at your disposal. So it's basically adding on to a database now that is up to something like 600 buildings, 60,000 users or occupant survey responses. So it's pretty robust. This is the largest database in the world of this kind of information. So this is how it's done. We go from a notification of email, get the occupants to respond to the web-based survey, goes into the server, and then it produces automated reports, output of these things. And so these are the categories, the categories that are covered, you know, not only the basic IEQ ones that I talked about here, but also, you know, other things like office layout and office furnishings and cleaning and maintenance. And there's lots of comments that get generated as well. And drill down menus when people aren't satisfied, they can tell us why they're not satisfied. So there's just a wealth of information that comes out of this. So this is an example page where we answer these questions on the 7-point scale here, from very satisfied to very dissatisfied. For each of those categories, there's a series of questions. And then we get these kind of histograms as a basic output here, showing, you know, the satisfied, you know, 25% satisfied, and 58% dissatisfied for this particular study. And then there's a benchmarking capability here. So the blue dots here, or the red dots, are actually our benchmark for our, in this slide was a little bit older, so it's 52,000 responses. And then the candidate building, in this case the Brower Center, which is right down off of campus here, how that scored relative to our benchmark. And you see it actually scored very well on all things except, of course, this one, which is a really common thing that we see. The acoustics aren't so good in a lot of these buildings. And here's some statistical output of the results in a kind of a scorecard format. So this is a way of rolling up this information, very important to get to this level. So the energy part of it is shown here. This is just a standard report of the Energy Star rating system that you get for a building. This is one that we've actually studied quite a bit, the Capital East End project in Sacramento. And so you can see the score up here. This is a score of 0 to 100. And you have to get 75 on that score in order to get a label to put on your building. And then there's, these scores are based on the EUIs, basically the source EUI, energy use intensity here. And you can see where this building was stacking up quite low compared to the label, and way low compared to the national average, of course. So that's a very nicely done building. In fact, it's an underfloor building as well. So that's why we were studying it so much. And then you get, of course, all these other useful information here. I'm going to just change this thing to be on. Okay, so that brings us to the real meat of what we want to talk about today, and that's what we call the PMP Wireless Toolkit project. So our goal here is to develop and demonstrate a practitioner-ready PMP toolkit that does all those things that the PMP calls for, and more, actually. And so the way we're approaching that is by, getting a robust data acquisition system using wireless technology, and then to develop some application software to go with it that does the analysis, visualization, and it can deliver results in near real time. A key issue here, and this is where SMAP comes in, actually saved our bacon, as a matter of fact, to make this actually achievable. This is sponsored by CEC and CIEE, and one of our most exciting projects, at least for me, for a long time. So this is really interesting stuff. So this is how it's made up. And you saw the poster. There's a paper copy of that poster back there you can look at again. But this shows the kind of broken down components. So this device here is the stratification tree and pressure measurement here that you saw on the other cart. Very easy to use, lightweight and all. Our goal, of course, is to get rid of all these multiple motes because we had limitations on I/O capability here. So we're looking to make this all work on one mote, which I'll talk about in a second. But then there's all these other sensors that we need to support now. So here's power monitoring here. Here's the acoustic meter. There's a lighting sensor on here. There's globe temperature, air velocity. These are little desktop kinds of monitoring stations that we can put all over the space and gather all of these kinds of measurements. And then we have a buffering database here that we use to collect this data on the floor. And then you'll see in a moment how that's all handled. And then the idea here is what happened is that we got to the point where shipping that big heavy cart around the country, as wonderful and beautiful as that it ended up being a lot more expensive than we thought and a lot of hassle. So we realized that we really need to make this thing truly portable so that you can take it on an airplane with very little problem. Not as carry-on. No, you can't do it as carry-on. And plus all the motes and everything else, yeah, you get in a lot of trouble there. So our current work is we're using the latest dust technology in their starter kit, these evaluation motes here, and we're building a board for this so we can accommodate all these different sensors that we have and make a multi-channel mote out of it. Then it's just very simple, straightforward, communicating over the serial bus into the mote and getting the data up and out of the network. So, these are the obvious advantages of this. We really love to have location awareness. We don't think it's quite ready for prime time, but that's coming, and so we see the future in that, and that would be a tremendous benefit for this kind of application. Reduce a lot of the tedious work that's required to log where you're making measurements in a building. So how does this all work? So there's a pretty simple overview diagram, and probably obvious to a lot of you techies here how this all works. But basically, we have all the sensors and wireless network down here. We have the buffering database where we store it on site here, and then we ship it in a lot of different ways. But we've been using the cellular network mostly. Works very well on 4G for not only getting the data out, but also communicating to our server here with laptops in the space or remotely or whatever. We also have the capability for BMS data, because we want certain kinds of pieces of BMS data, not everything, not a huge amount, just to supplement the data that we have from the wireless system. All that goes into the application server here, and thank God for SMAP, we now have a real database, robust database to work with, and gives us some really good response times. And of course, these guys are developing things every day, some new feature that we find useful. So we're really enjoying that collaboration. This is just some photos of carts in action, different buildings that we put these things in, and we've done these studies in. These are the wireless ones over here. So this is kind of our pre-prototype version of the all wireless system. This is the older cart in various buildings. So now I'm going to focus on the application software part, because despite all the nice things I said about wireless technology, when it comes down to it, we don't care. We just need some kind of wireless technology that is reliable enough to be able to deliver the data that we need. But really, when the rubber meets the road here, it's the application software that's going to make the difference in whether this system really flies or not. So we have just a few mock-up screens, so you can see where this is work in progress, actually. So I'm just showing you the way we're thinking this is going to look. And so you have all these tabs for all those categories that I talked about earlier are all listed here. And so now we're just on this project page, which is really just a data entry kind of a page. So that's a simple example. Then for each of those categories, then we have a page that looks something like this, where we can actually set up all these different levels of filtering, basically, and aggregation, and then produce results over here, visualization results of the comparison to metrics and looking at data in more detail, what have you. Lots of ways to use this capability. We think this is all pretty critical to making this whole system work. So here's an example, of course, of trending, and right out of SMAP. SMAP allows us to do this quite nicely without having to make a new application for it, and very robust, lots of channels here and zooming and the whole thing that you need for a trending application. This is another example. These are all just examples of what we foresee that we're going to be building. This is a way to overlay the results on the floor plate, so you can really tell which part of the building is behaving poorly or well against another part of the building. So that's a key capability. And then these are more the nitty-gritty kind of stuff that we like to know in order to diagnose things and understand more about how the building is working. So this is some examples from our underfloor air work. And in this particular chart is kind of a new way to present thermal comfort data, where we show the stratification over on this side here, and then the occupied zone temperature. In this case, because it's stratified, it's an average temperature. And then lay it on this map here, which is really a comfort envelope. And this peaky one here is the one that we've developed out of our thermal comfort research to show that, in fact, stratification can actually be quite high as long as you're in this temperature range, as opposed to the ASHRAE standard, which shows this very simple rectangular area here. So we think that needs to be improved, that the standard should be revised to consider stratification. But this is real data here, by the way, and you can see what's happening here. This is all down here in the cooler part of the comfort envelope. This is not unusual. Ed and we have been studying this for a long time and finding that overcooling is a significant problem in this country, and a major potential for energy savings. So that's as well as comfort. Then there's another way to look at these things with these contour diagrams, you know, where we can actually look at, you know, a pictorial view of what the temperature distribution is in this case, the supply plenum. There's some other ones here, the stratification profile. So now you can compare this. We have the data out of the BMS. We can compare it to the set points, see how well this thing is actually controlling, and how the temperature in the space compares to that set point. Another variation of room temperature data is shown here, just a histogram to see, you know, whether the system's sized well or it's controlling poorly or well or whatever. You know, you can pretty much see if it gets out of range here a predominant amount of time or not. And then there's a whole next level of this. Oh, I covered up that word, sorry. Which is really data-driven models here. And this is kind of data that we can collect with some cases BMS data, in some cases wireless data. A lot of times the information that we need to get is not actually covered by the BMS. Of course, you know, fan performance is one of them, as Craig here knows quite well. A lot of times you can't get that data out of the system that you need to create charts like this. So this is an opportunity to look at a component level, you know, how these components are performing. In this case, the supply fan. In this case, the economizer. Is it really performing like it should? And in this case, a chiller, showing basically a model of the chiller performance. Okay, so where we are to date, we're working in parallel with hardware and software developments. Basically, we've kind of finished with our pre-prototype field testing work, and now going to focusing really on the hardware development, you know, signal conditioning, sensor calibration, building these I/O boards. This is what we're involved in right now. On the software side, we've done a lot of integration with SMAP already, but we want to take advantage of all the cool new things that Stephen and Andrew are coming up with, so we'll continue to work with them on that. Pretty much finished with our metadata database here, and now we're really focusing on this data analysis and visualization software. And then finally, I want to just mention this part because, as I showed in the Occupant survey, eventually you get to a scorecard kind of a level, and that's really what we want to do here. And we don't quite know how to do this yet. This is part of the research attached to this project. We want to be able to roll all of this stuff up into a way that can make a really clear set of metrics to evaluate, and so that you compare across buildings and to benchmarking and all of that. So I think that's an important future goal of ours to get to that point. So what's next is, like I mentioned, just continuing hardware and software development through the spring, and then we go to field testing. So this is a kind of a unique part of this program that we're really excited about, and that is we signed up 3 of our CBE partners to actually take these prototypes out into real buildings and really give it the stress test, basically. Kick the tires, see how it works, and give us a lot of feedback. So I think that'll be a major accomplishment in getting these in their hands and seeing how they like it. And then, of course, we're looking for commercialization opportunities. You know, obviously, this isn't going to go anywhere if it doesn't get out of the lab and get out into industry somehow, probably through commissioning agents, energy service providers, whatnot, as either a service or maybe a product. We don't know exactly what yet, but we're interested in, of course, pushing that forward as well. So that's the end. So I can take some questions if you like.
Thanks, Tom. I'm gonna start off with a question. I have a question on that latest version of the cart. I wasn't sure whether that was a completely battery powered or AC powered.
It's all battery powered.
Okay,
yeah.
great.
Yeah, that's right.
Okay, we got a lot of questions. We'll start with Dave here.
Okay, great talk, Tom. Thank you. I had a question about the cart. As you move it around the space, it appeared that you had some fixed sensors, wireless sensors, and then the cart has wireless sensors. Doesn't the mesh get tangled as you move it around the building, or does that impede your motion, or how do you deal with that?
It actually recovers amazingly well. Yes, but it is reconfiguring as you move around, for sure.
And you don't lose data as you move at that
we don't.
rate?
Yeah, and it's good. And we were surprised, actually, because you had, on the cart, we have so many motes on there. You know, we were concerned that having all those motes reconfiguring at the same time would be a serious problem, as opposed to one mote on there. But it didn't seem to be. It seemed to worked just fine.
Those are dust motes.
Yeah, these are dust motes.
You showed the opportunity for saving energy through eliminating overcooled buildings. How does that correlate with your surveys? How do the occupants see that? Do they see the buildings also as being overcooled, or do they think it's comfortable?
Well, if you look at the occupant survey, the benchmarking, let's see if I could go to that, actually. It's a good question, Ron, and one that we talk about all the time. And so if you look at the thermal comfort benchmark here, it's right at 0. So it's not at 1 or 2, you know, which we'd like to see. Like a lot of these other ones are like 1.5, you know, the average scores on here. So it's always around, you know, 0 basically, and all the buildings are pretty close to that benchmark, actually. So that tells us that, you know, it's kind of a balance between dissatisfied and satisfied, that certainly there's room for improvement. But whether that's always overcooling or not, I mean, Xiangwei and Ed can answer that question probably better than I can.
Some of the problem is overcooling. It's about 6 times more common than overheat.
Yeah. Okay.
Question here?
Yeah.
Yeah, also on the energy saving, so looks like there's a lot of potentials for this. Do you have any numbers for savings versus the cost of implementing the system?
For cost of what?
The cost of implementing or deploying a system, like hardware cost, service cost.
You mean implementing this methodology?
Yeah, just maybe a rough idea of how much savings the customer.
Yeah, no, we haven't really looked at that. I'm sorry. We don't have those numbers at this point. That's one of the things we hope to learn out of these field studies. You know, how efficient can we make it? You know, how efficient actually is it to do this stuff? And there's really, you know, not really a good comparison other than research studies, because, you know, traditionally we haven't done this many measurements, you know, in a field monitoring situation like this. So we're kind of in new territory in that regard.
Continuing on that line, in terms of the energy costs, do you have any idea, or can you just give us a quick guideline about the cost of lighting energy use versus heating, air conditioning energy use versus any of the other aspects in there?
Well, they usually break down roughly, very, very roughly. There's lots of numbers about this, of course, you know, and like 30, 30, 30, 30 lighting, 30 plug loads, and 30% HVAC energy, which comprises cooling and heating. So you can go to the DOE energy book, and they have a lot of, you know, sort of these gross level numbers like that. So that's kind of the balance, yeah, something in that range.
Yeah, I was curious about the meaning of the questions that are asked to the respondents when they're asked to judge their satisfaction with the conditions in a building. The example you gave asked something like, how satisfied are you? And I was thinking of myself as a potential respondent. I wouldn't know necessarily whether I should answer how satisfied I am this minute or today or this month or this year. And I'm wondering whether you're giving respondents any tighter prescriptions as to the framework within which they answer?
Yeah, the general answer is that we're looking for people's kind of integrated response to how they feel about it over some period of time. And of course, they will be influenced to some extent by the time of the year that they're taking it and things like that. A lot of times we actually do it in the winter and the summer. We have another form of survey called the Right Now survey, where we're looking for exactly what you're talking about, how they feel at that particular moment. And usually we couple that with these desktop monitors so that we can see what the actual physical measurements are showing. Yeah.
Okay, do we have any more questions? Okay, that's it. Well, thank you very much, Tom. Great talk.
All right. Thank you.